Welcome, my friends. In this video, we will continue to graph transformations of sine and cosine. Here I have the untransformed version of both sine and cosine. You should remember that sine starts at 0, 0 and increases from there, and cosine starts at 0, 1 and decreases from there. Each graph has important points at a quarter of the period, and the period of sine and cosine is 2 pi, so 1/4 of that would be pi over 2. So we have important key points on the graph at every pi over 2 radians, either at pi over 2, pi, 3 pi over 2, or 2 pi. Here is the general form of a transformed sine function. Of course, you could replace sine with cosine. We could have a value for a, which is a change in amplitude of the function. That would change how far the function oscillates from the center, which is called the midline. If we had a value for c, that would represent a horizontal phase shift. We would have a shift to the left if c is positive, and a shift to the right if c was negative. D represents a shift in the midline. If d is positive, the midline will be shifted up, and if d is negative, the midline will be shifted down. This video will focus on functions that have a value for b, a value multiplying x inside our function. A value for b represents a change in the period of the function. The new period can be found by taking 2 pi and dividing by b. Let's take a look at some examples. Say that we are asked to graph y equals cosine of 1/2 x. In this example, we have a value for b, a value multiplying x on the inside of our function. That means we have a change in period. You can always find the new period by taking the original period, which is 2 pi, and dividing by b, the value multiplying x inside your function. In our case, we will have 2 pi divided by 1/2. We can reciprocate the denominator and multiply, so that we have 2 pi times 2 over 1, which is equal to 4 pi. That means that the period of this function is not 2 pi, but it's actually 4 pi. Let's think for a moment why 2 pi over b can be used to find the new period. Recall that the untransformed version of cosine or sine has a period of 2 pi, so once the inside of the argument reaches 2 pi, the function will start to repeat itself. So the question becomes, what value for x would we have to input into the function in order to get 2 pi? Well, we would have to input 4 pi. If we inputted 4 pi, we would get 4 pi times 1/2, which would be 2 pi. So once x reaches 4 pi radians, the entire inside of the function will reach 2 pi and start repeating itself. Therefore, the new period is 4 pi, because that's what we have to input into the function to get the inside of the argument to reach 2 pi, which would represent one period. In general, we can always find the value by taking 2 pi and dividing by the coefficient b, and that will always tell us the new period. Now, on any trigonometric function, we have important key points on the graph at every quarter of the period. This is what I've been calling the increment. Typically, for the untransformed cosine or sine function, the period would be 2 pi, so 1/4 of that is pi over 2. So we typically have important points at every pi over 2 radians. But for this function, we already found that the period is 4 pi, so we will instead have important key points at 1/4 of that, which would just be pi. 1/4 of 4 pi is just pi. Let's start to graph our function. Typically on a cosine function, we would start at the point 0, 1, which is still the case here. The change in period has not changed our starting place, so we have the point 0, 1 on our graph. What will change is our increment. Typically we would increment to pi over 2 to have our next important point. But since our period is 4 pi, our increment is 1/4 of that, which is just pi. So we will have important points on the graph at every pi radians. So if you start adding pi, we will find the important points. We will have pi, 2 pi, 3 pi, and 4 pi. Once you've added the increment 4 times, that will represent one period of the graph. Now just follow the general shape of cosine to fill in the remaining points. Typically, cosine starts at a maximum and then decreases from there. So at pi, the next increment, we will be at a 0. At 2 pi, we will have decreased to the minimum of -1. At 3 pi, we will have another 0. Finally, at 4 pi, we will be back to the maximum of 1. Connect the dots, and we have drawn the graph of y equals cosine of 1/2 x. Let's try another problem. We are asked to graph y equals -2 times sine of 3x. Now we have a value for a value multiplying the function. A value for a represents a change in amplitude, the amount that the function will oscillate around its midline. The absolute value of a is the amplitude, so in this case, the absolute value of -2 is +2. That means that this function will oscillate between -2 and +2. Note that we also have a negative sign on our function. The negative sign indicates that this function will decrease at the beginning of its period. Typically, the sine function would start at 0, 0 and increase from there, but this one will instead start at 0, 0 and decrease. We also have a change in period, because we have a value for b multiplying x on the inside of our function. We can find the new period by taking 2 pi and dividing by b. In this case, we will have 2 pi divided by 3, so the new period is 2 pi over 3. As I've been saying, we will have important key points on the graph at every quarter of the period. This is what I've been calling the increment. So we can find the increment where we will have important key points by multiplying the period by 1 over 4. 2 pi over 3 times 1 over 4 is equal to 2 pi over 12, which reduces to pi over 6. So we will have important key points on the graph at every pi over 6 radians. Let's graph the function. Typically, a sine function starts at 0, 0, and there's nothing in our function that would change that, so we will still start at 0, 0. Next, we are going to want to complete at least one period of the graph, so therefore we will need to add the increment 4 times to find the x values to which we can plot our key points. Adding pi over 6 once, we will have pi over 6, then we will have 2 pi over 6, 3 pi over 6, and 4 pi over 6. If you'd like to, you can reduce these values, but sometimes I prefer not to, because I think it's a little bit easier to leave them all with the same denominator. Next, we can think about the general pattern of the sine function to fill in the missing points. Typically, sine would start at 0, 0 and increase from there, but we have a negative sine function, which means that we will do the opposite. We will still start at 0, 0, but instead of increasing, we will decrease. Also note that since we have an amplitude of 2, we will decrease not to -1, but actually to -2. So at pi over 6, we will have the point pi over 6, -2. Then at 2 pi over 6, we will have increased back to 0. So we have 2 pi over 6, 0. Then we will increase to 3 pi over 6, 2. And then finally, we will be back down to where we started, at 4 pi over 6, 0. We can connect the dots to draw our sine function. This is the graph of y equals -2 times sine of 3x. Let's try this problem. We have y equals 5/2 times sine of 2/3 x plus 1. So now we have three things going on in this function. We have a value for a, which is going to represent a change in amplitude. We have a value for b, which is going to represent a change in period. And we have a value for d, which represents a change in the midline. The amplitude is the absolute value of the value multiplying the function, which in this case is just 5 over 2. The midline has been shifted up 1 unit because we have a value of 1 for d. So that will shift up the entire function 1 unit. We can find the new period by taking 2 pi and dividing by our coefficient b on x. 2 pi over b is 2 pi divided by 2 over 3. We can reciprocate the denominator and multiply, so that we have 2 pi times 3 over 2. 2 pi times 3 is equal to 6 pi, so we have 6 pi over 2, which reduces to 3 pi. The period of this function is 3 pi. We have important key points on the graph of a trig function at every quarter of the period, which I've been calling the increment. 1/4 of our period of 3 pi is going to be 3 pi over 4. Let's draw our graph. Since we have a shift in midline, I like to draw that in a dotted line, so I have drawn y equals 1 in a dotted line. Typically, a sine function would start at 0, 0, but since we have a shift in the midline, we will instead start at 0, 1. We would like to graph one period of the sine function, so that means we must have 4 increments. So start adding the increment 4 times to find our values for x that we will have important key points at. Adding 3 pi over 4 once, we have 3 pi over 4. Adding 3 pi over 4 again, we would have 6 pi over 4. Then we would have 9 pi over 4, and finally 12 pi over 4. These are the x values that we will have important key points on the graph. The sine function starts right at its midline, at 0, 1 in this case, and then will increase to its maximum. The maximum will be 5/2 units above the midline. 5/2 plus 1 is going to be 7/2. So at 3 pi over 4, we will be up to 7/2. Then at 6 pi over 4, we will be back to the midline of 1. So we have the point 6 pi over 4, 1 on the graph. At 9 pi over 4, we will be 5 over 2 units below our midline, which would be at -3 over 2. so we have the point 9 pi over 4, comma, negative 3 over 2 on the graph. At 12 pi over 4, we will be back to where we started, at 1, so we have the point 12 pi over 4, comma, 1 on the graph. Connecting the dots in the pattern of a sine function, we have the graph of y equals 5 halves sine of 2/3 x plus 1. Okay, let's look at one final problem. We have y equals 3 times cosine of 2x plus pi over 2. In this case, we have a value for a multiplying the function, which represents a change in amplitude. We have a value for b, which represents a change in period, and we also have a value for c, which represents a phase shift, either to the left or to the right. The amplitude is the absolute value of a, which in this case is 3. That means this function will oscillate between 3 and negative 3. Now in this problem, we have both a phase shift, indicated by the plus pi over 2, and a change in period, indicated by the 2 multiplying the x. If that's the case, then the value for c will not actually be the correct phase shift. There's one small adjustment that you will need to make first. If you have both a phase shift and a period change, indicated by a value for c and b, you must factor out the coefficient on x to properly identify the phase shift. The coefficient on x is 2, so that means we must factor out a 2. So we have y equals 3 times cosine of 2, and then we will write the rest of the function on the inside here. So we need to think to ourselves, what do we need to write in parentheses so that we have factored correctly? Well, we must have x plus pi over 4. Multiply it out just to check to make sure that it works. 2 times x is indeed 2x. 2 times pi over 4 is indeed pi over 2. If you're struggling with the factoring step, just remember that factoring is really just dividing out some value. So in this case, we are dividing out 2. So all you have to do is take pi over 2 and divide by 2, and that will give you the pi over 4 that we need in the factoring step. At this stage, we can identify the period, which is 2 pi divided by the value that you factored out, which is the same value as b. 2 pi divided by 2 is just pi, so this function has a period of pi. This function also has a horizontal phase shift of pi over 4 units to the left. Recall that when we have a value added on the inside of the function, that indicates a phase shift to the left. So this is a shift of pi over 4 units to the left. If you had not factored first, you may have incorrectly concluded that the phase shift was pi over 2 units to the left. So that is why we must factor first. The increment is where the key points fall, and is always 1/4 of the period. In this case, the period is pi, so the increment is 1/4 of that, or pi over 4. Let's start to graph our function. Typically, the untransformed version of the cosine function would start at its maximum of 0, 1. In this case, we have an amplitude of 3, so we would instead typically start at 0, 3. But in this case, we have a horizontal phase shift pi over 4 units to the left, so instead of starting at 0, 3, we will start at negative pi over 4, 3. From here, we can increment 4 times to find x values to which we can find important points on the graph. Incrementing 1 time, we would be at 0. And then incrementing again, we would be at pi over 4, and then 2 pi over 4, and then 3 pi over 4. Since we have incremented 4 times, that will create one period of our cosine function. From here, we can follow the general form of the cosine function to find the other key points. Cosine typically starts at a maximum and then decreases from there. So at the next increment at 0, we'll be at 0. At the next increment, we will be at the minimum, which is negative 3. So we have the point pi over 4, negative 3 on the graph. At the next increment, we will be back at 0. So we have the point 2 pi over 4, 0. Finally, at 3 pi over 4, we will be back at the maximum of 3. We can connect the dots to draw our cosine function. This is the graph of y equals 3 times the cosine of 2x plus pi over 2. Alright my friends, that finishes part 2 of graphing transformations of sine and cosine.